hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment the rangefinder's elevation is pi force, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Now, I didn't draw a picture on the last one. I should have, but I definitely want to draw a picture on this one so that we can understand it. So we've got a rangefinder over here. One of those things that just measures distances and angles. And it is 500 feet. And this is to the liftoff point. This is the liftoff point. We have a balloon rising in the air. There's our balloon. Oh, such a pretty balloon. It's going this way. Rising in the air. And at the moment the rangefinder's angle of elevation is pi force. Now I will tell you this is really so not drawn to scale, but I have this tiny little space to put in here. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? All right, so here's our diagram. We've got the angle. We've got what the angle is increasing by. We're given one side of a right triangle. Right, this would form a right triangle. But no other sides of the right triangle. Or are we? Or can we find them? Well, let's write down our variables first of all. So we have, let's call this x. That's the adjacent side. It's adjacent to our angle. So let's call this y. Y is the opposite side. We don't need the hypotenuse right now because we got two sides. That's good enough for me. So we're going to not use that side. We've got theta, right? That's our angle of elevation. And I think that's all I can think of at the moment. So I think that's it. All right, so identify which, if any, of the variables in the problem will remain constant. X will remain constant. Right? The rangefinder's not going for a walk. Right? The liftoff point's what the liftoff point is. So X is going to be 500 feet. Right? We're given that the rangefinder's 500 feet away from the liftoff point. The other distances are changing, but not that one. Right? So now we want to find, identify the rates that we're given and the rate we wish to find. We're given d theta dt. That was 0.14 radians per minute. We want to find how fast the balloon is increasing. We want to find dy dt. Technically, we know dx dt. It's 0. But if we just plug in the constant value, we don't have to worry about dx dt. All right, so we've got an angle and we've got two sides of a triangle. And we've got the opposite and adjacent side. Sounds like a tangent problem to me. So tangent theta equals opposite over adjacent, y over 500. I kind of like moving the 500 on the other side rather than dealing with a 500 in the denominator. I don't want to really necessarily have to use the quotient rule, and nor do I really like a coefficient of 1/500. So let's just multiply both sides by 500. And then we have 500 tangent theta equals y. And that just looks a whole lot nicer, doesn't it? All right, so now let's take the derivative. We're up to step 5. And I'm going to scroll this page up a little bit because it'll be a little easier for me. All right, so we have the derivative of 500 tangent theta, would be 500 secant squared theta d theta dt, right? This would be a chain rule. So we have to take the derivative of theta with respect to time. Equals dy dt. Oh, look at that. Our dy dt is already isolated. Right? So now we just need to plug in some values. Right? We've got d theta dt. We need secant squared theta. Right? Well, let's think about what that would be. Right? This is pi fourths. Let's put it on a coordinate plane. Unit circle. Right? Pi fourths. So a right triangle with one angle that's pi fourths means it's got two angles that are pi fourths. This is the 45, 45, 90 right triangle. It's an isosceles right triangle. So not only were we given x, we were given y. It's also 500 feet. At least at the moment in time where we wanted to know how fast the balloon is rising. Not that we need the value of the opposite side, but we do need secant. And so secant is just the reciprocal of cosine. It's hypotenuse over adjacent. So secant pi 4, let me plug in the value there. So this would be 500 secant squared pi fourths d theta dt equals dy dt. Right, because it's at the moment, that's a d, the moment that our angle is pi fourths. And so that the secant pi fourths is just going to be the square root of 2 over 1 or the square root of 2. So this is a pretty easy equation to evaluate. And so let's just simplify the rest of this. And I'm going to put dy dt over here. dy dt equals 500. Secant squared theta is now, or secant squared pi fourths is now the square root of 2 squared. And d theta dt is 0.14. And this is really easy to simplify because we've got 1,000 times 0.14. Just move a decimal place over 3 places. This is going to be 140 feet per minute. Right, so our measurement, our rate of change for the units for the angle would be radians per minute, but 500 is in feet. This is going to be in feet. Right, this is a linear measurement. So let's write in what that means. So let's explain our answer there. So the rate of change, or let's put the balloon is rising. I like that better. The balloon is rising at a rate of 140 feet per minute when the angle of elevation is pi fourths radians. And there we go. So you should be able to interpret your answers as well. So another problem done. And this one I think was a little bit of a tricky one. All right, but if you've got an angle and a side, be thinking a trig ratio. And use the trig ratio that matches the sides you're given. I want to know about the opposite. I know the adjacent. Got to be tangent. Right? Don't make it cotangent. Right? Stick with the easiest one you can do. All right. So thanks for watching. Bye for now.